Guys, welcome to my YouTube channel. Let's talk about the hybrid orbitals. We talked about the sp2 orbitals and also sp3 orbitals that actually happen in many molecules, and also we talked about the sp orbitals with two mixing of 2p orbitals with the s orbitals. And today I want to discuss about these hybridizations or these molecular orbitals forming molecules in chemistry. Okay, so let's talk about the specific molecules. Ethylene, we have talked about ethylene before. Ethylene has the Lewis structure like this. It has two of these sp2 orbitals. If you look, so the idea, let me just try how to say, explain it in real short. If you count the surrounding atoms and the size with the lone pairs, so lone pairs and surrounding atoms on a carbon, you could, or any heteroatom, any other atom that other than carbon, you could determine its hybridization. So if it's two, you would have an sp orbital. If it's three, you would have sp3 orbital. If it's 3, you would have sp2 orbitals, and if it's 4, you would have sp3 orbitals. So here you have 1, 2, 3 surrounding atoms for this carbon. That's why it's sp2. Also the same for that other carbon. So you have two sp2 going to actually overlap together. The one between the two carbons gives sigma bond for these two carbons, and the one between the carbon and hydrogens gives the sigma bonds of CHs. Okay, we have two types of bonds: sigma, which is written like this in Greek, and pi is written like this in Greek as well. And pi bond is either the second bond in a double bond or the second and third bond in a triple bond. So this bond kind of is a pi here. So let's talk about, we talked about the shape. The shape of that molecule would then be, if this is a plane, you could actually assume that the molecule, I have a model of, this is ethylene. If you assume the molecule in a plane, you have the 4 hydrogens in that plane, and it would be like this on the top and on the bottom. Like if this is the sp2 and you have those you have this px and py mixed with the s to give you 3 sp2s, you would have one remaining p on each carbon, and that remaining p on each carbon would be on the top and on the bottom. On the top it would overlap laterally to form this, a kind of cloud, and also on the bottom to form another cloud. And this pi cloud, we call it the pi bond, and we could see that it kind of forms the nature of reactivity for this molecule. So a pi bond on the top and a pi cloud in the bottom. So there is these two pi clouds form the one pi bond that we talked about, the double bond. Okay, that is how ethylene molecule is reactive. These two clouds of the pi or the double bond is responsible for that. So there is one pi bond and 1, 2, 3, 4, 5 sigma bonds. Okay, so you could just go on and write that down to see how that works. Okay, so there is this one pi bond and 5, 1, 2, 3, 4, 5 sigma bonds. Okay, let's talk about yet another molecule other than ethylene that has a triple bond in it. Okay, and that's acetylene. Acetylene, the Lewis structure for acetylene is like this: a carbon, triple bond, and hydrogen, and another hydrogen. Now if you look, you've got a carbon here, 2 surrounding atoms, and also a carbon, 2 surrounding atoms. No lone pair, so that would be 2 and make an sp. This is just a linear molecule that you see in my hand. Now 2 of these bonds are pi bonds, so you have a second and a third pi bond in a triple bond, and in that it would be this carbon having an sp orbital and the other carbon having another sp orbital that would form the sigma bond and then the pi bonds would then be the one in the z direction and the one in the y direction, coming out actually towards you, and these two going back. The one that's coming forward would also form a pi, the ones in the back as well. The one in front would do so as well, just like you see for ethylene, and the ones in the bottom as well. So you would have 4 of these pi clouds, and then they would actually form 2 pi bonds, but it doesn't stay at this stage. If you have 4 of those pi bonds, one in the top here and one like this in the front and in the back. So if you have 2 of those, what happens is that they would all mix together to give you a sort of blanket, okay, that kind of wraps around the molecule like this. So it gives you a symmetrical cylindrical blanket that sort of encapsulates the 2 carbons, okay? That's the kind of a triple bond in acetylene. It's kind of a very symmetrical cylindrical blanket around that molecule. And that gives you, for acetylene, it gives you 2 pi bonds, and you will have 1, 2, 3 sigma bonds. Now I want to move on to other more challenging examples and talking about the exact same idea. Let me just get rid of this, and we will talk about a molecule that is very much bigger. Okay. So on the carbons, there is rare species usually that have lone pairs. If there is a species that has lone pairs, I would actually want to mention that, or I would draw that, or it would be in the problem. But if it's the other atoms like oxygens, heteroatoms, nitrogens, phosphorus, any other atom than carbon, you should actually consider. So the oxygen needs 2 bonds, it's group 6, to be satisfied, and it has 2 lone pairs, also the 2 bonds. Now this OH, and that's the same story for the VHs as well, you could assume it like this. Okay, just for the sake of simplicity, we write it down as OH, but we know that there is a sigma bond between the two. So there is 1 bond here, 1 bond here, 2 bonds, oxygen is satisfied, so 2 lone pairs must be there. Now let's count and see what is the hybridization on each of these atoms. You have 2 hydrogens that is surrounding the carbon and 1 carbon. So 3 atoms surrounding that carbon, no lone pairs, this is sp2. Also 1, 2, 3 surrounding this central atom, no hydrogens, no lone pairs, so also sp2. 3 hydrogen atoms and 1 carbon, 4, no lone pair, sp3. For this one again, 3 surrounding atoms and no lone pair, no hydrogens, sp2. For this one, there is 1 surrounding atom and 2 lone pairs, also sp2. For this one, there is 2 hydrogens surrounding it, and this carbon and this oxygen surrounding it, that's sp3. And for this one, 2 atoms, the hydrogen and this carbon surrounding this oxygen, and 2 lone pairs, so that's sp3 as well. Okay, you could also count the number of sigma bonds. For counting the number of sigma bonds, I would just draw the skeleton with just lines, because I just need the connectivity, not the double bonds. So that would be this sort of notification for this, and then 1 branch down here and 1 branch up. I don't do a double because I don't care, I just need the connectivity. So there is 4 of these, 2 branches make 6. Also, I don't want to miss the hydrogens that actually are attaching to carbon or heteroatoms, so I just count them and add them up for the sigma bonds. There are 3 here and there's 5 here, so 8, it would be 14 sigma bonds. And I could just say I have 2 pi bonds, so that's the number of sigma bonds and the number of pi bonds that we kind of notice. Let's move on to yet another example. Let's move on to this example right here. Carbon, 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 a carbon, a carbon, a carbon, so CH3, CH2, CH, CH, CH2, 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 V double bond O, CH3, and then the connectivities are sort of like this. So that's the molecule. And I want to talk about the hybridization first, and I'm going to use a trick here instead of just counting. If you have a carbon or any other atom and there is no double bond involvement, it's not attached to a double bond or a triple bond, you could make sure that it's sp3. If that's not the case, then you should count the surrounding atoms to figure out whether it's sp or sp2. So this one, no engagement, no engagement, no engagement for all of this, so they are all sp3 because there is no double or triple bond involvement in them. You could check them once, check one of them randomly. This one, for example, 3 hydrogens, 1 carbon surrounding this carbon, so that's sp3. Okay, for this one there is 3 atoms surrounding it, so that's sp2. And for the high oxygen, we need to figure out the number of lone pairs, because there are 2 bonds, so it should be 2 lone pairs, and there's 1, 2, and 3, so it's also sp2. So that's the hybridization. Now how do I do the connections, like the sigma bonds and the pi bonds? For the sigma bonds, I want to look at I want to redraw essentially the molecule in the skeletal form of the molecule, so to speak. There is a pentagon right here, and there is a sort of branch like this, and there's one that goes here for the oxygen. Again, we don't care about the double bonds, we just need the connectivity, and one goes down here. So the 5 and 3 makes 8, 2 branches, that's 10. Let's count the number of hydrogens that are connected, not to miss anything. So there are 6 here, 2 and 2, that's 4, so it makes 6 and 4, 10. And there are other 6 here, that makes 16, and it's 26 sigma bonds. And I just want to mention that I do also have a pi bond that makes it like this. So there's 1 pi bond, 26 sigma bonds for this molecule, and that's where I want to move to yet another example. Let's see how much time I have. I still have enough time to go into more and more examples. Let's do this one. CH2, CH, carbon, CO, CH3, CH3. This goes below this bond here, so I just kind of show it like this. CH2, CH2, and a CH3 connected here. Okay. Oh, let's see. Let's make sure that you guys can see it. CH2, CH2, CH3. Let's see. Yep, now you can see it. Okay, now let's talk about the hybridization. There is, when there is no involvement of, there's no involvement of a pi bond, I could safely say sp3. So sp3, 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 all of those just sp3, except for these 2 that have, this one has 1, 2, 3 surrounding atoms, so sp2. And if you put the 2 lone pairs here, this guy has also sp2 configuration. Okay, so that's the hybridization. Let's talk about the number of pi bonds. The number of pi bonds, I should do the connectivity. Let's do this sort of, you kind of see a book, like it's these are going to be useful here, a book like thing here for the connectivity. That's that, so that's this, and there's sort of a triangle or a bridge on the top, of that. So I'm just going to do that. Let's just get rid of those little, okay. So that's this. There is one goes up, down here, we don't care if it's double, and then 1 here. So there is 1, 2, 3, 4, 5, 6 for the booklet that we just told you, 2 for the breach, that makes it 8, and 1, 2, 3, 4 for that makes it 12, plus the number of hydrogens. So 12 plus, let's see how many hydrogens. I have 6 here, then I have 4 here, makes it 10. So 6 and these 4 makes it 10. And then I have another 6 that makes it 16. So it would be 28 sigma bonds and only, again, only 1 pi bond. Okay, that's this example. Let's now move on to yet another example while I have time. Let's do this example. So going towards the hybridization, there is no atom that we could find that there is no engagement with, how to say, with the double or triple one. So none of them, neither of them or none of them is a sp3 hybridization. For the nitrogens, there is the 3 bonds, so there should be the 1 lone pair consideration, and I move on to not accounting the doing the hybridization. 1 lone pair, 1 surrounding atoms sp. That's the same exact story for all the nitrogens because all of them look alike. Also for these 4 carbons, they are all alike, so if I work out 1, I could actually expand to all others. There are 2 surrounding atoms, no lone pair, so sp2, just like this. And then these 2 carbons, 1, 2, 3, so it's sp2. The same story for this one, also sp2. Let's also do these 3 carbons, sp, sp, sp. If the carbon is engaged or any atom is engaged with a triple bond, that would be most likely sp. So that's the hybridization. Let's talk about the number of pi bonds. I should do the connectivities. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigma bonds. These are the connectivities. If I just connect the 2 carbons and carbon nitrogens, okay, that's the connectivities, okay. And also the pi bonds, I could just highlight them with red. 2 here, 2 here, 2 here, 2 here. That would be 4. That would be 4, 2 to 8, and 1 in the center. That would be 9 pi bonds as well. Let's see if I could still do one more example. Let's, if I move quickly, I could do one more example, and we will wrap it up here with the hybridizations and hybrid orbitals discussion. Okay, let's do that. Let's do it for this molecule: carbon, 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 nitrogen, CH2, CH3, and then also CH3, and then there is oxygen. Oh, my bad. And oh, let's see if you could, yeah, you could see this and CH3 also over here. Make sure that you guys can see that, still see that. Yes, there, that is that one, a double bond, and then an H. This is also CH. So let's go on and talk about the heteroatoms first. There is a lone pair here because of the 3 bonds, and there's 2 lone pairs here because of the 2 bonds. So both nitrogen and oxygen are normal. There's no hyperactivation or anything like that. So we will talk about the other atoms. If there is involvement with a double bond like these 4, the hybridization we have to talk. If not, for all the other atoms, we could just say they are sp3. So sp3, 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 oh, sp3, this sp3 here, you could see that, maybe not this one, so I just put sp3 on the other side. And then also sp3, we could just check to see if we have not missed anyone. Like this one, there is one lone pair, 2 carbon surrounding and 1 hydrogen surrounding for 4, that makes sp3. For this one, there's 1 hydrogen, 2 carbon surrounding, so sp2, 3 carbon surrounding sp2, again 3 carbon surrounding sp2, 1 nitrogen, 1 oxygen, 1 carbon, 3 surrounding atoms, sp2. For carbons, there's no lone pair, so just you count the surrounding atoms. So that's this. If we want to count the number of sigma bonds, there's again a pentagon, 1 branch over here, 1 branch over here, and 1 branch over here. So 5 and 2 and 2 and 1. So that's 5 and 5, 10. The number of hydrogens are thus 3 and 2, actually 3 and 3, 6. And these 4 would make 10, and with that 3, 13. So 23 sigma bonds. And if you just count the 2 pi bonds, that would be 2 pi bonds as well. So that's it. I want to wrap up this video with this molecule here, and that's actually it for recognizing the hybrid orbitals in different molecules.